Hello everyone. Today we'll start discussing a new topic within the kinematics chapter. Uh, so it's called rigid body rotation. From the name of it, it may seem like this is this is a topic which should come within the purview of the subject dynamics, but uh, uh, but as we'll see, it is very much a part of mechanics of solids. So, in order to motivate the discussion for this rigid body rotation, what we have to do is we have to uh, go back to the slide of one of the earlier lectures. So I want to bring your attention back to this particular formula that we had arrived at earlier. So this was within the topic of quantification of deformation. So one of the earliest parts of the lectures. So we'll write this down again and proceed from there. Okay. So what we have is the d small x vector is equal to d capital X vector plus the d capital X vector dotted with the gradient operator and that operating on the displacement vector. Now for our current purpose, we'll find it useful to write the equivalent index notation of this particular equation. So the left hand side of this is very easy. This is just the d small x vector, which can be simply written as dxi. Similarly, the first term is also very easy to write like this. Now for this last term, let me just write it down and then I'll discuss. So I'll write it as dxj del ui del xj. So you see here earlier, so in that, let me go back to that earlier slide once more. So if you see here, I had put this bracket here. So this dx vector dotted with the gradient operator, that was like a scalar operator. This was like a vector. The gradient operator is also like a vector, and we have a dot product between these two things. So it is like a scalar. So you see, if you just for a moment forget about this ui, it is as if this dxj, it is clubbed with this del xj. So because the index j is repeated here, what you basically have for this is dx1 del x1 plus dx2 del x2 plus dx3 del x3. That entire operator operating on this ui. So we can think of it like this: dxj del xj, that is equivalent to dx1 del x1 plus dx2 del x2 plus dx3 del x3, and that is exactly equivalent to dx vector dotted with the gradient operator. Okay, so we understand that whatever we had obtained earlier in our quantification of deformation topic, this is the equivalent statement. So why are we writing like this? What is the advantage? Well, you'll see in a moment that because we have this thing now, del ui del xj, and if you now shift your focus just to this partial derivative, here, del ui del xj, then again I am writing this in my right hand column, the del ui del xj. You see, if you just look at it, at this thing, how many free indices does it have? I and j. So there are two free indices. Correspondingly, we can conclude that this is a tensor of order 2. And because it is a tensor of order 2, it can be very well be represented as a 3 into 3 matrix. Now you know from your first year studies of matrices that if you have any matrix, that can be represented as the sum of the symmetric and the antisymmetric parts, and we'll do exactly that here, that kind of a decomposition here, by writing this as dxi. First term remains unchanged, and for the second term I'll write the dxj as it is, but this del uy del xj, what I will do is I will decompose it in this fashion: del uy del xj plus del uj del xi. This is the first part, and I will adjust whatever I have added extra in the previous line by writing this thing. So you see what I have done here. Whatever the del uy del xj was here, that is actually broken up into this half del uy del xj, this half del uy del xj. Together these two make up this. But here I have added this del uj del xi together with the half extra, and here I have adjusted that with the minus half del uj del xi. So this line here is exactly equal to whatever was present in the earlier line. Now you see this particular combination, the del uy del with the half del uy del xj plus del uj del xi, that we have already we have come across this particular term earlier. And what was that? We just look back, so you see half del uy del xj plus del uj del xi, that we had chosen to define as the infinitesimal strain tensor. So that is exactly the term that we have encountered right now. So we recognize that half del uy del xj plus del uj del xi is nothing but the strain tensor. It is the strain tensor itself. And when I write the strain tensor, I implicitly mean that it is the infinitesimal strain tensor or the small strain tensor. The other part here, this one, the half del uy del xj minus del uj del xi, this part is referred to as the rotation tensor. So it is as if this entire thing is somehow denoting the rotation. So before we can discuss anything further on the rotation tensor, I'd like you to note down that corresponding to this little discussion we had about the del uy del xj being a 3 into 3 matrix, and that being decomposed into the symmetric and the antisymmetric part, that is exactly what we have managed to do here, because this thing is symmetric. It is symmetric because you can interchange the I and j and it would not make any difference. You can see here, if you interchange, if you replace the I by the j and the j by the I, so this entire, and here also if you replace the j by the I and the I by the j, this entire term remains unchanged. However, this part, if you replace the I by the j and the j by the I here, similarly if you replace the j by the I and the I by the j, then this, the whatever the resulting term is, that is the negative of this thing. So because you will have del uj del xi minus del ui del xj, and that is the negative of what I have written here. So this part is the antisymmetric part. So that is what I meant here. So any 3 into 3 matrix can be subdivided or decomposed into its symmetric part and its antisymmetric part, and it is nothing special with the del ui del xj. If you have any matrix like say A having 3 rows and 3 columns, you can have this kind of a decomposition. All right, so what we are saying is that from this del ui del xj, the symmetric part, it is giving us the strain tensor, the infinitesimal or the small strain tensor, and the antisymmetric part of the del ui del xj, that is giving us the rotation tensor. This is very, very important. I repeat, because it is so very important, that the symmetric part of the del ui del xj, that gives me the strain tensor, and the antisymmetric part of the del ui del xj, that gives me the rotation tensor. Okay. Now we go to the next slide and we note down that this rotation tensor, usually it is denoted by the capital Greek letter omega. So the rotation tensor, so this is the capital omega symbol. Now based on this, what we can do is we can quickly go back to this earlier equation, to this equation that we had written earlier, and we can write this in terms of the epsilon and the omega. So we can so d small xi is equal to d capital Xi plus d xj epsilon ij plus d xj capital omega ij. Before proceeding any further, as I had mentioned in one of the earlier lectures, we must always, whenever we write anything new in index notation, it is important that we should check with the consistency of the order of the tensors. On the left hand side we have just one free index, which means this is a vector or a tensor of order 1. This here also one free index, same index I as in the left hand side, so very much consistent with whatever we have here, and this also is a vector or a tensor of order 1. Now this entire entity, whatever it may mean physically, but at least mathematically speaking, we are very sure that since the j is a repeated index here and we have only one free index I, this entire term ultimately is just a tensor of order 1 because there is only one free index. Similarly, for this third term on the right hand side, we have j to be repeated and we have only one free index I. So this entire term, whatever it may mean physically, there is no doubt that mathematically speaking this is a tensor of order 1, and it is also denoted by this single free index I. So everywhere the free index is given by I, and this entire equation is very much consistent mathematically. Okay. Now what we want to do is we want to see explicitly about this omega ij. It is this, but in terms of the matrix representation, what does it look like? So before I write anything down, I want you to think for a moment about what could possibly be the diagonal elements of this matrix representation, of this equivalent matrix representation for the rotation tensor. So we have already noted that the omega ij, the rotation tensor, is antisymmetric. If you have an antisymmetric matrix, then by definition the diagonal elements must turn out to be 0, and you can verify that yourself. So what we can say here is, or what we can write down explicitly here is that no matter what happens to the off diagonal terms, the diagonal terms must be 0. So this is like this. Okay, now note that this is an antisymmetric matrix. So this term here in the second row and the first column should be the negative of what is present in the first row, second column. So this should be the diagonal element is 0, and this one should simply be del u2 del x3 minus del u3 del x2. And finally, for the third row, we know that it should be the negative of this first row, third column. So this should be minus del ui del x3 minus del u3 del x1. And this term here that I'm going to write in the third row, second column should be the negative of the second row, third column, which is this term. So it should be minus half del u2 del x3 minus del u3 del x2, and the diagonal element, the third row, third column element, should be 0. Now you note one very interesting thing. If you just discount this negative sign, then in terms of independent entities, how many of them are there in this matrix? See, this 0 is there, of course, but this is the negative of this, this one is the negative of this, and this one is the negative of this. So among the non-zero elements, we have basically just 3 independent elements. So even though this is a 3 into 3 matrix and it is the equivalent matrix representation of a second order tensor, but effectively in terms of the actual entities, there are only 3 of them present here. This one, and this one. And we can exploit this fact to write it in a slightly more clean fashion like this. Zero minus omega 3 omega 2 omega 3. So when I'm saying omega this time, I mean the small Greek letter omega. So this is the capital Greek letter omega, this is the small Greek letter omega. This is minus, this is 0, this is minus omega 1, this is minus omega 2, this is 0. There is no hard and fast rule as to why I am choosing this to be minus and this to be like this, but this is generally adopted for some sort of convenience. You'll see in a moment. But you see, what I'm basically writing this is that this minus omega 3 is equal to this thing, this omega 2 is equal to this thing, and the minus omega 1 is equal to this thing, and the rest of it is just following from there. Now, what is the advantage of writing like this? So one advantage is that we can explicitly recognize the fact that we need only 3 independent elements, non-zero elements, the omega 1, omega 2 and omega 3, to denote this 3 into 3 matrix. Now because there is this kind of only 3 element picture, it perhaps gives us an indication that maybe it should be possible to somehow re-represent this kind of a 3 into 3 matrix in another form, maybe perhaps using vectors, which actually involves only three independent quantities. Okay, so how can we perhaps do that? So in order to do that, we'll go to the next slide. But before going to the next slide, uh, what uh, what I want to do is uh, I I want to proceed towards a direction which will help me to motivate this kind an explanation for why this entire thing is perhaps referred to as the rotation tensor. Why the name rotation? I mean, for the other one we are calling it a strain. Why this is rotation specifically? Okay, so let me go to the next slide. Try to motivate that discussion. So we have this equation dxi is equal to d capital Xi plus dxj epsilon ij. I'm just repeating what I had written in the previous slide, and capital omega ij. Now you consider a special case. Consider the special case when epsilon ij, the strain tensor, is perfectly equal to 0. So we are saying that there is no strain in the body. If there is no strain in the body, then forget the maths. If I just tell you that there is no strain in the body, then what should be your immediate conclusion? Your immediate conclusion should be that perhaps if there is no strain, then perhaps no deformation is taking place within the body. But if there is no deformation taking place within the body, does it prevent us from saying that there should not be any translation or rigid body rotation? It does not. Like if I let me give you a physical example. Okay, so I have this pen here which I am using to write on my pen tablet. Now this is fairly a rigid body. Now I am holding it like this, and suppose I rotate it like this. This is a simple rotation like this. I can also rotate it like that. I can do various things. I can not rotate it and just move it like this, a simple translation, but I'm choosing to rotate it like this. Now when I'm doing this, you can understand that 2 points which are present in this body, they are not moving relative to each other. This is very, very important to note. So you have 1 point here and 1 point here. They are not moving relative to each other when I'm moving the entire body or rotating the entire body like this. So this is the kind of physical scenario where I'm saying that there is no strain present within the pen. So there is no strain present anywhere within this pen when I am moving it. But the fact remains that I am actually moving it. So there is displacement. Displacement is not 0, but the strain is 0. This is very, very important to note. Okay, so if we go back to our discussion, so this is what I mean by this epsilon ij equal to 0. So under this special consideration, I have just this. All right. Now I have already seen that the capital omega ij in the previous slide, that can be represented by this kind of a 3 into 3 matrix having effectively just 3 independent elements. Now this is where it gets interesting. You see, this thing here, it is just one it is like one repeated index here. So some kind of tensor operation is going on here. Okay, however, whatever is going on here, it can be equivalently represented in a slightly different fashion in this way. I'm falling back on the vector representation again, plus, okay, so this is the trick part. So here I will write the omega vector. I'll just explain it in a moment. And this is the vector cross product with dx vector. So this is x, this is my x, and this is the vector cross product. So what I'm saying is, whatever you have from here, that can, so you first of all you understand that there is a vector here, there is a vector here, no problem. The vector cross product of two vectors, that should be a vector. There should not be any doubt about it. You all know this. In the previous line also, we have already concluded that whatever this entity is, mathematically it should be a tensor of order 1, and a tensor of order 1, we know that is nothing but a vector. So as far as the consistency of the order of the tensors is there, these two are perfectly fine. Question is whether they're equal or not. We'll come to that, but you just note that this is a vector and this also is a vector. That much is okay. It is also very nice to see that we have the dxj vector here, that is also somehow present here. The question is, what is going on with this little trick here? So you can actually verify this longhand. I am not going to do the longhand thing. I'll just ask you to do this here by noting that the omega vector, that we understand to be equal to this thing, omega 1, omega 2 and omega 3. This column vector in matrix representation, and you all know this, that the dx vector, the equivalent matrix representation is nothing but dx1, dx2 and dx3. Now so somebody very clever figured out that if you can actually do the vector multiplication of these two things, the resulting entity is exactly the same if you do the complete expansion of this term, noting of course that noting of course that the omega ij contains terms like this. You can actually do it. So if we go back to our slide here, the way that you can actually verify this is you can substitute or you can just repeat the j here with in this form, dx1 omega I1 plus dx2 omega I2 plus dx3 omega I3, and then you can actually put different values of this I as 1, 2 and 3. Now you'll have 3 components there. Similarly, you can expand this out using your high school mathematics. You can carry out the cross product, and you will finally see that whatever you are obtaining here and whatever you are obtaining here will be exactly equal. Okay, I won't spend any more further time on this. Rather, I'll try to see if I can motivate a physical interpretation of this. So first of all, you note that we are working under the special consideration that epsilon ij is equal to 0. So the strain is 0. When the strain is 0 and you are ending up with this sort of an expression, you note that this vector quantity, whatever it is perpendicular to this as well as it is perpendicular to this. I repeat, suppose you have any vector cross product like A cross B, you know that the resulting entity must be perpendicular to both the original vectors. So it must be perpendicular to this, it must be perpendicular to this. So the result of this, okay, so whatever this thing is, it is perpendicular. We understand that this is perpendicular to a dx vector. Okay, now let me just write that down, that the vector must be perpendicular to the dx vector itself. Now furthermore, you understand that because we are operating under small deformations, suppose we understand that this magnitude of this omega vector is this and this, both these magnitudes are small. This is a very important line. It's a very short statement, but it's a very powerful line that we're going to write. So if both the magnitudes of this vector and this vector are small, then we can understand that the magnitude of this quantity, this vector, that must be also small. Okay. Now, if this is true, then can we not conclude that dx vector is almost equal to the d capital X vector? So think for a moment about what we have concluded. First of all, we started with epsilon ij equal to 0. So we are working under no strain. Then we are saying that we are managing to write it like this, and because overall the deformations are small, then this omega cross dx term must be small, and from that we are concluding that the distance or the relative the difference in the position vectors of two neighboring points in the deformed state, that is what is meant by this d small x vector, that must be almost equal to or approximately equal to whatever the thing or whatever the relative position vector was between two neighboring points in the undeformed state. And that is exactly what is meant by rigid body motion. But this has of course been brought about by the rotation of this thing omega, and we are saying that it is the rotation because it is perpendicular to the position vector connecting two neighboring points. So if we have the undeformed state like this, you remember that we had taken our point P here and the point Q here, and this vector between them, that was our dx vector, because this position vector was x vector and this was x plus dx vector that we had written in one of the earliest classes. So this relative vector from P to Q, that is dx vector, and we are saying that the overall motion or overall displacement is such brought about through this omega that it is perpendicular to this dx vector, and that is why it is like a rotation. So you have this kind of a thing and it's just rotating about like that. So as a result of this special kind of displacement, together with the fact that the epsilon ij is equal to 0, we have this kind of a thing, that the relative motion between, or the relative displacement even in the undeformed state, that doesn't change. All right. So this was a fairly long lecture, but we have completed this particular topic on rigid body rotation in one shot, and in the next one we'll go to a very important topic. In the next part of the lecture we'll go to a very important topic, principal strains. Thank you very much.